Section: Introduction. In this section, we explore reinforcement learning (RL) algorithms for fine-tuning large language models (LLMs) using verifiable rewards, particularly focusing on mathematical reasoning tasks. This area has gained attention with the introduction of models like OpenAI's O1 model and DeepSeek R1. The most common method for post-training LLMs has been proximal policy optimization (PPO), but it requires an extra critic network, adding complexity and computational demands. Given the deterministic nature of LLMs, we believe that many of PPO's advanced features may not be necessary, prompting interest in simpler RL algorithms. Recent works have revisited reinforced style methods, including Remax, RLOO, GRPO, and Reinforce++. Other approaches, like reward-ranked fine-tuning, RAFT, generate multiple responses for each prompt, filter out incorrect ones, and fine-tune the model on the accepted samples. Preference-based methods, such as SFT-based contrastive learning and DPO, optimize based on pairwise comparisons. Among these, GRPO is notable for its effectiveness in enhancing LLMs for math reasoning tasks, although its specific advantages are not well documented. In contrast, RAFT is recognized for its simplicity and consistent performance. In our project, we examined three methods. 1. RAFT, which is a basic RL algorithm for LLM post-training. 2. Vanilla Reinforce, a simpler version of PPO that does not use a critic model. And 3. GRPO, which samples multiple responses and calculates relative advantages based on normalized rewards. A key distinction between GRPO and RAFT is that GRPO includes both accepted and rejected samples during training, while RAFT only uses positive samples. Interestingly, our initial experiments show that the performance difference between these methods is smaller than expected, with RAFT even converging faster in the early stages of training. We also found that certain negative signals, like prompts with all incorrect responses, can harm performance, while reward normalization has little effect. To investigate these dynamics, we conducted ablation studies with Qwen and Llama models across various reinforce variants. Our findings indicate that RAFT's performance is competitive with GRPO, especially in early training, but it eventually limits exploration due to its focus on positive samples. We discovered that GRPO's advantage comes from its ability to filter out harmful prompts. In response to our findings, we propose a new variant, Reinforce Reg, which filters out prompts with all correct or all incorrect responses. This method achieves performance similar to GRPO while demonstrating better efficiency. Overall, our insights emphasize the significance of sample selection over the specific algorithm used in reward-based LLM post-training. The code for our project is available for further exploration. Section Summary. In this section, we investigate reinforcement learning algorithms for fine-tuning large language models, particularly focusing on mathematical reasoning tasks. We find that simpler methods like RAFT, which uses only positive samples, perform competitively with more complex algorithms like GRPO, and highlight the importance of sample selection over algorithmic complexity in reward-based post-training. Section: RAFT. In this section, we describe the RAFT algorithm, also known as rejection sampling fine-tuning. We follow a three-step process. 1. Data collection. For a set of prompts, we gather multiple responses from a reference model for each prompt to create a pool of candidate responses. 2. Data ranking. Rejection sampling. We evaluate each response using a binary reward function to determine their quality. We keep only the highest scoring responses, which form our positive sample dataset. 3. Model fine-tuning. We then adjust our current model to improve its performance based on the selected dataset. We also mention a related method called STAR, which retrains from the original model each time and generates only one response using a greedy approach, unlike the rejection sampling in RAFT. STAR also suggests including the answer in the prompt for tougher questions. Next, we discuss the policy gradient and reinforce methods. We simplify our explanation by treating the action as a whole initially. The policy gradient algorithm aims to optimize a specific learning goal, where we update the model parameters using a method that incorporates the policy gradient. In practice, we collect data using the old policy and use it to compute a stochastic policy gradient for updates. To speed up training, we often perform multiple updates in mini batches and apply importance sampling to adjust for distribution differences. However, we must be cautious, as this can introduce high variance if the policies diverge too much. To stabilize training, we can use clipping techniques from PPO. We also extend our loss function to account for each token in the autoregressive model, treating each token as an action. For GRPO, we modify the loss function to use an advantage function instead of the reward, which helps reduce variance in our gradient calculations. Lastly, the DPO algorithm uses pairwise comparisons of responses to optimize a contrastive loss. We can iteratively generate new responses and label preferences to enhance model performance using self-generated data. Section Summary. In this section, we describe the RAFT algorithm, which involves three main steps: collecting candidate responses from a reference model, ranking these responses using a binary reward function to create a dataset of high-reward samples, and fine-tuning the current model to maximize the log likelihood over this dataset. We also compare RAFT with related algorithms like STAR and discuss the use of policy gradient methods and importance sampling techniques to stabilize training and improve performance. Section: RAFT++. In this section, we explore RAFT++, which we recognize as a hybrid algorithm that can operate off policy by taking multiple steps on the replay buffer during each iteration. We extend the original RAFT by incorporating importance sampling and clipping techniques, resulting in a similar loss function that focuses on training only with the highest reward responses. For our experiment setup, we concentrate on mathematical reasoning tasks, primarily using the VERL framework. We utilize the Numina math dataset, which contains around 860,000 math problems along with their correct answers, sourced from various educational contexts, including Chinese high school exercises and international math competitions. We conduct experiments with both the Quen 2.5 Math 7b base and LLAMA 3.2-3b instruct models to ensure generality, employing the default chat template and using a chain of thought prompting strategy. Regarding hyperparameters, we adhere to the recommended setups in the VERL framework for reinforce, GRPO, and PPO training. The hyperparameters for RAFT and RAFT++ align with those in the GRPO script. Specifically, we use the Atom W optimizer with a learning rate of 1/1,000,000th. We sample 1024 prompts per iteration and generate 4 responses for each prompt in RAFT and GRPO. The mini batch size is set to 512, and the models can generate up to 4,096 tokens during training. More detailed scripts can be found in our GitHub repository. For evaluation, we assess the model's reasoning capabilities using the Math 500, Minerva Math, and Olympiad bench datasets, excluding the AMY 2024 benchmark due to its limited number of problems. Our preliminary experiments indicate that results on this benchmark are quite variable across algorithms. We primarily use average accuracy at 16, generating 16 responses per prompt with a temperature setting of 1.0, and we measure the average accuracy as our metric. Our findings reveal that RAFT and RAFT++ perform comparably to deep reinforcement learning methods, with only a small performance gap. We summarize the test accuracy of models trained with various algorithms in a table. Notably, RAFT, which is one of the simplest algorithms, achieves competitive results compared to more complex methods like iterative DPO and deep RL approaches. For instance, with the Quen 2.5 Math 7b base model, vanilla RAFT achieves an average accuracy of 49.9%, surpassing iterative DPO's 48.2% and nearing PPO's 51.8%. With the added importance sampling and clipping, RAFT++ improves to 52.5%, closely approaching the best deep RL method, GRPO, which has an average accuracy of 53.9%. A similar pattern is observed with the LLM 3.2 to 3B instruct model, indicating the robustness of RAFT and RAFT++ across different architectures. Interestingly, we find that Reinforce performs significantly worse than RAFT++ in the Llama setting, with average accuracies of 23.4% and 27.5%, respectively. This suggests that relying solely on final answer correctness for negative samples may limit the effectiveness of negative feedback in RL training. We plan to conduct further ablation studies to better understand the impact of negative samples in RL training. We also note that applying distribution correction and clipping enhances the performance of vanilla RAFT, leading to the stronger variant, RAFT++. Our analysis of the learning dynamics shows that both RAFT and RAFT++ improve the model's reasoning ability through online updates, with RAFT++ converging faster and achieving higher final accuracy. In our ablation study, we evaluate a variant that uses importance sampling without clipping, which underperforms compared to vanilla RAFT. This finding contradicts previous research suggesting that clipping is rarely necessary. We hypothesize that while clipping may be infrequent, it becomes crucial when the ratio of the new policy to the old policy deviates significantly from 1, as unbounded updates can disrupt the on-policy assumption of policy gradient methods, leading to instability and reduced performance. Section Summary. In this section, we explore RAFT and its extension RAFT++, highlighting their hybrid off-policy nature and the application of importance sampling and clipping techniques, which enhance performance. Our experiments demonstrate that RAFT++ achieves competitive accuracy in mathematical reasoning tasks, outperforming more complex methods while showing robust performance across different models. Section. RAFT++ achieves faster early-stage convergence but is surpassed by GRPO in later training. In this section, we observe that RAFT++ shows quicker early-stage convergence but is eventually outperformed by GRPO in later training phases. Our analysis reveals that RAFT++ learns faster initially, but around the 100th iteration, its growth rate noticeably slows down. Ultimately, GRPO surpasses RAFT++ in final model test accuracy. To understand this slowdown in RAFT++, we will conduct ablation experiments focusing on the impact of missing negative samples. In our ablation study, we aim to uncover the reasons behind our earlier findings. We will explore why RAFT++ is faster initially but falls behind later, and the significance of negative samples. We will also investigate what contributes to GRPO's superior performance compared to vanilla Reinforce. We start by analyzing policy entropy and KL divergence for RAFT++ and GRPO. We find that RAFT++, which relies solely on positive samples, experiences a rapid decline in policy entropy, more so than GRPO. This pattern is consistent across both Quen and Llama models. Once the entropy stabilizes at a low level, RAFT++'s performance improvement slows down, likely due to reduced exploration with low entropy policies. Meanwhile, GRPO continues to improve, highlighting the importance of negative samples in maintaining exploration and preventing performance stagnation. To further explore the relationship between policy entropy and reward learning, we apply a technique that uses asymmetric clipping ranges. This adjustment helps stabilize policy entropy during training, allowing an enhanced version of RAFT++ to outperform the original in later stages. We also examine the key factors behind GRPO's success, focusing on the use of negative samples and reward normalization. We conduct controlled experiments to assess the impact of these components. Our findings indicate that removing incorrect samples significantly improves performance, while removing correct samples does not yield much benefit. Additionally, we find that normalization alone does not enhance rewards and may lead to instability. Ultimately, we conclude that GRPO's strength lies in its ability to reject low-quality samples, particularly incorrect ones, rather than in normalization techniques. We refer to the variant that removes both correct and incorrect samples as Reinforce Reg, which serves as a competitive baseline for reward-based policy optimization in large language models.